Okay, welcome back. This is Mr. Hassan's Maths channel. I'm now answering question number 25, which is the final question from this paper of the specimen paper from the 0580 IGCSE Cambridge paper 2. This is for the specimen paper B for the new syllabus from 2025, the non-calculator paper. And here we are asked to first of all simplify these. It's like all about index form, this question, and exponential equations, as you'll see in part B. So first of all, it says simplify 2xy to the power of 0. So you got all of this to the power of 0. Now what we should understand is anything to the power of 0 is going to equal 1. Okay, that's true for anything to the power of 0. And you know, we can kind of prove that, for example, if we have, for example, say a to the power of 3 divided by a to the power of 3. We know from our laws of indices that we subtract the powers when you're dividing numbers in index form. So you have a to the power of 3 minus 3, which is a to the power of 0. And we also know that a to the power of 3 divided by a to the power of 3, they cancel out, leaving you 1. So a to the power of 0 is equal to 1. So this is kind of a small little proof that anything to the power of 0 will equal 1. Okay? Anything to the power of 0 is going to be equal to 1. And so there's the answer to part 1. Now part 2, we have this like this fractional index and this fraction inside here. Now what you should try to do always in a question like this to make your life easy, if you can simplify what's inside that bracket first, then do so. So we have 81 over 3. Now 81 over 3, well, we know, if you didn't know that 81 is 3 times 27 and you weren't sure about that, well, you should be sure that 81 is divisible by 3 if you wanted to make sure. So we know that 81 is divisible by 3 because for the numbers 3 and 9, this works for the numbers 3 and 9. If the digits of the number give you a sum which is divisible by 3, then the number itself is divisible by 3. If the digits of the number give you a number which is divisible by 9, then the number itself is divisible by 9. This number 81, if you add the digits, you get 9. 9 is divisible by 3, so we know 3 will go into 81. And if you weren't sure how many times it goes in or whatever, you can set up a little short division. 3 into 8 goes 2 times, okay, because 2 3s are 6, and remainder 2. 3 into 21 goes 7 times, 3 7s are 21, and that's the exact number of times. So 81 over 3 is going to give you 27. And when you have m to the power of 8 over m to the power of 2, it's like m to the power of 8 divided by m to the power of 2. And as we learned just now, as mentioned, when you're dividing numbers in index form, you subtract the powers. That's going to be m to the power of 6. M to the power of 6. You can think about it. You write m times n times n, 8 times, and then 2 times. 2 of the m's will cancel, left with m to the power of 6. Okay, and this is raised to the power of 2/3. Now we've got to deal with this fractional power. Okay, this fractional power. Now to deal with the fractional power, what we have to understand, very important, is that a number to the power of a fraction, okay, can be written in surd form as the mth root of that number to the power of the denominator. So the numerator is, sorry, the other way around. What am I talking about? My bad. The nth root of a to the power of m. The denominator is the root and the numerator is the power. The denominator is the root and the numerator is the power. Okay, so it's very important for you to understand it, that the denominator is the root and the numerator is the power. Okay, very, very important for you to understand that. So what I'm going to do here is I'm going to split this up into 27 to the power of 2/3 times m to the power of 6 to the power of 2/3. Now what I like to do is, with my numbers, I like to treat them in this surd type of form. So I'll write this as 27 under the root sign, but this is going to be the cube root, because that's the denominator of 27 to the power of 2. The cube root of 27 squared. And with algebraic terms, I prefer to write them in a form that we know. For example, if I have a to the power of m raised to the power of n, then we know that this is a to the power of m times n. Okay, this is one of the rules of indices that we should know, and we can kind of prove it. Like if I have 2 cubed to the power of 4, this is like 2 cubed times 2 cubed times 2 cubed times 2 cubed, which is 2 to the power, if you add the powers, 12. So 3 times 4 is 12. It's like when you multiply the powers, you get the answer. Right? So if you have something raised to a power to another power, you just multiply the powers. So here, what I have to do is I have to do m to the power of 6 multiplied by 2/3. And we know that 6 times 2/3, if you multiply them, that cancels, you get 4. So you got the cube root of 27. The cube root of 27 is 9. Sorry, it's 3. I'm talking about. I'm getting the final answer here. The cube root of 27 is 3. We should know our cube numbers, very important. And that's going to be, so that's going to be 3 squared times m to the power of 4. Because this is going to cancel. You have 2 times 2, which is 4. And 3 squared is 9. So you have 9m to the power of 4. So some of these laws of indices, we need to know them very well. Okay. And it's something very important for us to realize. Okay. So that's something that is extremely important for us to know. So there we have the answer to part 2 of 25 part A. Now we're going to go on to 25 part B, which is about this exponential equation, right? Now, when we want to solve an equation involving exponents like this, where x is in the power, an exponential power, or an exponential equation, sorry, is one where x is in the power, the unknown is in the power. Then we have to try to express all the numbers in terms of the same base. Now, in IGCSE, all of these type of questions can be solved by making the bases the same. So we got to look at the numbers we have. We have 32, we have 2, and we have 4, basically. So 1 over 4, we can deal with that. So all of these can be expressed as 2 to the power of something. This is 2 itself, this is 2 squared, and this is 2 to the power of 5. And we should know that. We should recognize the powers of 2. Like 2 to the power of 0 is 1, 2 to the power of 1 is 2, 2 to the power of 3 is 8, 2 to the power of 4 is 16, 2 to the power of 5 is 32, 2 to the power of 6 is 64. All right, those are numbers that we should know, that recognize them as the powers 2 to the power of something, right? We should know, some of these, and you can carry on. You can keep doubling them, like 128, 256, and so on. So you can see that that's very important for us to know, so we can answer questions like this easily. Remember, this is the non-calculator paper, so you can't just try different values. You have to know them. Okay, if you recognize them quickly, that's better for you. So I can express all of these as 2 to the power of something. So this 32 is 2 to the power of 5, but that's raised to the power of x. This is fine as it is, 2 to the power of x plus 3. And this is 1 over 2 to the power of 2. Okay, so I've rewritten all of these numbers in terms of the same base, which is 2. Okay, and now when I've done that, I can solve this equation a lot easier. So now we're using the same law that we learned up here, that when you raise something to a power, to another power, you multiply the powers. So I'll use that law here to write this as 2 to the power of 5x. And this is times 2 to the power of x plus 3 equals, now I'm going to use another one of the laws that we should know of indices, that 1 over a to the power of n is the same as a to the power of negative n. It's like a reciprocal. So 1 over 2 squared is the same as 2 to the power of negative 2. Okay, that's a very important rule that we should know. And for example, if I want to prove it, I can say, for example, a to the power of 3 divided by a to the power of 5. This is like a times a times a over a times a times a times a times a. 3 of the a's cancel, leaving you with 1 over a squared. Right? And we also know that a to the power of 3 divided by a to the power of 5 from our understanding from before is that we subtract the powers. So you have a to the power of negative 2. So a to the power of negative 2 is the same as 1 over a squared. Okay, that's a little proof for this law here. Okay, so 1 over a to the power of n is the same as a to the power of negative n, and vice versa. You can switch it around as well. So now I can combine these two together. As we know, when we multiply two numbers in index form, we add the powers. So this is going to be 2 to the power of 5x plus x plus 3. And that's equal to 2 to the power of negative 2. So I'm just going to get rid of, well, no, in fact, I've got space here. So that's 2 to the power of 6x plus 3 equals 2 to the power of negative 2. Okay, so we're getting there now. Okay, so why did I add these powers? Again, I can show you, if I have a to the power of, for example, 2 times a to the power of 3, it's like a times a, and then times a times a times a. So you see we have a to the power of 5. It's the same as adding these two together. Okay, so if the same base, you multiply two numbers with the same base, you can add the power. So that's what I've done here. So I've got 5. So from here and here. What I've done is I've combined these together by adding the powers to the same base. Okay. Now, when I have an equation like this, where I have, it's called an exponential equation. Now, both sides of this equation, they are both expressed with the same base. So if 2 to the power of 6x plus 3 is the same thing as 2 to the power of negative 2, that means the bases must be the same. 2 to the power of something must be equal to 2 to the power of the same thing. That means 6x plus 3 must be the same as negative 2. In which case, 6x is equal to negative 2. Take away 3. 6x equals negative 5. So I can divide both sides by 6. So x equals negative 5 over 6. So there's the answer to that part of the question. Okay, so this is all to do with exponential equations and indices. So we need to know our index laws. We need to know our powers of 2 and other powers as well. For 3, for example, you'd have 1, 3 to the power of 0 is 1, 3 to the power of 2, 1 is 3, 3 to the power of 2 is 9, 3 to the power of 3 is 27, 3 to the power of 4 is 81, and so on. You should know your powers, okay? So this whole question here is all about indices and exponential equations. Very important question. It was the final question of this paper. Now, other questions from this paper can be found in the playlist, which will appear in the top right of the screen at the end of this video. Other questions from the topic of indices and exponential equations can be found in the playlist, which will appear in this. And those questions will all be limited to the ones from the 2025 syllabus onwards. You can also see the older questions from the previous syllabi in the playlist over here. You can subscribe to my channel by clicking on this link. Thank you for watching and see you soon.